Part 1. What is conductivity? Conductivity is the measure of a material's ability to conduct an electrical current. In simple terms, it's the ease with which electricity flows through a substance. Some materials, like metals, are excellent conductors, while others, like rubber, are insulators, resisting the flow of electricity. The conductivity of water is a measure of the capability of water to pass electrical flow. This ability directly depends on the concentration of conductive ions in the water. These conductive ions originated due to inorganic materials such as chlorides, alkalis, carbonate unsulfide compounds and dissolved salts. Pure water is said to be a bad conductor of electricity. Normal water is said to have impurities from ions called minerals, etc. These ions are known to be responsible for the conduction of electric current in the water. Because the electrical current in water is transported by the ions present in them, the electrical conductivity is said to increase with the increase in the concentration of ions in them. Conductivity is directly proportional to salinity. That is, when salinity increases, the conductivity will also increase. When the temperature increases, the water's conductivity will also increase. The distilled water conductivity is 0.05 microsiemens per centimeter. Part 2. Units of conductivity. Siemens per meter, SM. This is the standard unit for electrical conductivity. It represents the conductance of a material or solution over a distance of 1 meter. In practical terms, it tells you how many Siemens S of conductance are present within a 1 meter length of the material or solution. In addition to Siemens per meter, you may encounter other units for conductivity, especially in non-SI systems or specific applications. Microsiemens per centimeter, microsiemens/cm. This unit is often used for water quality measurements, especially in environmental and water treatment contexts. 1 SM is equal to 1000 microsiemens/cm, so it's a smaller unit. Millisiemens per centimeter, ms/cm. Sometimes, you might come across this unit, which is equal to 1000 microsiemens per centimeter or 0.001 sm. It's used for materials or solutions with higher conductivity. Decisiemens per meter, d/m. This unit is less common but occasionally used, and it's equal to 0.1 Siemens per meter. Microsiemens per meter, microsiemens/m. Another less common unit, it's equal to 0.000001 Siemens per meter or 1 millionth of a Siemens per meter. Part 3. Types of conductivity. Electrical conductivity measures how well a material conducts electricity. Used for metals and solutions. Thermal conductivity measures how well a material conducts heat. Important for insulation and electronics. Ionic conductivity examines how ions, charged particles, move in materials or solutions, often in batteries. Electronic conductivity focuses on the flow of electrons in materials, especially in metals. Solution conductivity checks how well a liquid can conduct electricity, often in chemistry. Bulk conductivity looks at the overall conductivity of a material, considering all factors. Surface conductivity assesses how well a material's surface conducts electricity, used in electronics. Acid and base conductivity measures how well solutions conduct electricity based on their acidity or alkalinity, pH, important for water quality testing. Part 4. Factors affecting conductivity. Temperature conductivity generally increases with higher temperatures because it gives more energy to charged particles, making them move more freely and conduct better. Concentration of ions. Higher ion concentrations in a solution lead to greater conductivity, as more charged particles are available to carry electrical current. Type of ions. Ions with higher charge densities contribute more to conductivity, and their mobility affects it as well. Nature of the material. Different materials have varying levels of conductivity. Metals are excellent conductors, while insulators like rubber have very low conductivity. Impurities. Impurities or contaminants can hinder conductivity by disrupting the movement of ions or electrons. Pressure. Higher pressure can increase conductivity in some cases, particularly in gases. Electrode material. The type and quality of electrodes used in conductivity measurements can influence the readings. pH acidity or alkalinity. Solutions with extreme pH levels tend to have higher conductivity due to more ions. Electrolytes. Substances known as electrolytes significantly enhance solution conductivity by producing more ions. Part 5. Conductivity in everyday life. We encounter conductivity in our daily lives more often than we might realize. From the copper wires in our homes that carry electricity to power our appliances to the conductive touch screens on our smartphones, conductivity plays a vital role in modern technology. Part 6. What is a conductivity meter? A conductivity meter, also known as a conductometer or a conductivity probe, is a device used to measure the ability of a solution to conduct electrical current. It consists of a probe, electrodes, and a meter that displays the conductivity value. Part 7. How does it work? Conductivity meters work on a simple principle. They measure the electrical conductance between two electrodes immersed in a solution. As ions in the solution move in response to an applied voltage, the meter calculates the conductance and converts it into a conductivity value. Let us have a deep look into the explanation of the working principle of a conductivity meter. Components of a conductivity meter. 1. Electrodes. A conductivity meter typically consists of two electrodes, a pair of metal or graphite rods, plates, or cylindrical probes. 1. These electrodes are designed to be immersed in the solution whose conductivity is to be measured. 2. Sensor housing. The electrodes are housed in a sensor or probe, which is often made of non-conductive materials like plastic or glass to prevent interference from the sensor body itself. Electrolytic solution. 1. The solution under analysis, often referred to as the electrolyte, contains charged ions, either positively charged, cations, or negatively charged, anions, which enable the conduction of electric current. 1. The concentration of these ions determines the solution's conductivity. Applying electrical voltage. 1. To measure the conductivity, a small, known electrical voltage is applied across the two electrodes. 1. This voltage creates an electric field within the solution. Ions movement. 1. When the voltage is applied, it exerts a force on the charged ions present in the solution. 1. Positively charged ions, cations, will move towards the negatively charged electrode, cathode, while negatively charged ions, anions, will move towards the positively charged electrode, anode. Measurement of current. 1. As the ions move towards their respective electrodes, they carry electric charge with them, creating an electric current. 1. The magnitude of this current is directly proportional to the number of ions present and their mobility in the solution. Conversion to conductivity. 1. The conductivity meter measures the electric current and converts it into a conductivity value, usually expressed in Siemens per meter, SM, or its reciprocal, resistivity in ohm meters, or mil.m. 1. Conductivity is a measure of how readily the solution allows the flow of electric charge. Temperature compensation. 1. Conductivity measurements can be influenced by temperature variations. 1. Many modern conductivity meters include automatic temperature compensation, ATC, to adjust the readings based on temperature changes. 1. This ensures accurate and consistent results, even when working with solutions at different temperatures. Calibration. 1. To ensure accuracy, conductivity meters require periodic calibration using standard solutions with known conductivity values. 1. This calibration process adjusts the meter's reading to match the actual conductivity of the solution, accounting for any electrode or sensor drift over time. Part 8. Applications of conductivity. Water quality control. Conductivity measurements are vital in power plants to monitor water quality. They help prevent corrosion and scaling, ensuring efficient and safe operation of equipment, such as boilers, turbines, and condensers. Boiler efficiency. Maintaining proper water purity is crucial for boiler efficiency. Conductivity readings help detect impurities in boiler feed water, preventing scaling and corrosion that can reduce heat transfer efficiency. Steam quality. Conductivity measurements ensure that steam leaving the boiler is dry and free from impurities, which is essential for the longevity of turbines and overall power plant efficiency. Cooling systems. Proper water quality in cooling systems is vital to prevent corrosion and fouling in condensers and heat exchangers. Conductivity measurements help maintain efficient cooling. Ion exchange resin regeneration. Conductivity readings are used to determine when ion exchange resin beds need regeneration, ensuring effective removal of impurities from water. Corrosion prevention. Monitoring water and steam conductivity helps minimize the risk of corrosion, extending the lifespan of critical equipment and reducing maintenance costs. Environmental compliance. Conductivity measurements ensure wastewater quality meets environmental regulations, helping power plants adhere to discharge standards. Safety. Accurate conductivity measurements are crucial for safe and efficient power plant operation, detecting and addressing water quality issues to reduce the risk of accidents and equipment failures. Part 9. Conclusion. Conductivity is the unsung hero that powers our tech-driven world. It keeps things humming along smoothly and efficiently. As we look ahead to the future, understanding and harnessing conductivity's potential is key to making our world more electrifying and sustainable. So, stay curious and keep an eye out for how conductivity keeps shaping the world around us.